Morning. Do you have any questions? Do you see the practice question I posted for testing? Was it okay?
I think so. I looked through about half of it. I realized what time it was. I went to bed.
Huh?
But the first half was.
Okay. I realized I had some typo. I was typing up the solution, and then as I go, I made some calculation, my own calculation. Some of the page had the wrong number, and then the final one has the right number. But you can do your own calculation. If you already know the answer, you don't have to watch the whole. You can go different way. Okay, so this is today's attendance question. I want to know if you already kind of understand the idea of Macaulay duration as a calculation. The duration. I think last time on Tuesday we went over duration. The calculation of duration involved two concepts. One is Macaulay duration, one is modified duration. The first one we explained is the Macaulay duration is the weighted average of the payment time, the time of the payment. So you would want to find out the weighted depend on the total premium value, and then every payment is premium value. The payment premium value divided by the total premium value. That's the weight for that payment time. So that's the Macaulay duration calculated based on the cash flow. And there's another way of calculating Macaulay duration is we might want to, some of the question asks us to calculate modified duration. In fact, if you can calculate modified duration, you can calculate Macaulay duration. So you can go vice versa. If you already have the Macaulay duration calculated divided by 1 plus I, that's the modified duration. Or if you're able to calculate the total present value as an interest rate function of the interest, then you can find that function and then find the derivative of that function, the negative derivative p prime I divided by p of I. That's the modified duration. So if you already have modified duration multiplied by 1 plus I, that's Macaulay duration. So have the present value formula also made it possible. So it's kind of vice versa. Some people are more comfortable with calculus and differentiation. So they will go by, I mean, sometimes it may even easier. For me, I did a couple of calculus, negative p prime I over p of I. That's a kind of a calculus way of looking at modified duration. But then many of the finance people, they prefer look at individual cash flow and their present value calculation. So they would prefer calculating Macaulay duration and then divide it by 1 plus I. So if you are in the investment class or finance class, they had that modified Macaulay duration calculated first, divided by 1 plus I, that's modified duration. I think this example kind of follow that idea. For the Macaulay duration of perpetuity, I calculated present value function with respect to I. Because for perpetuity, the present value is simply 1 over I, and then you differentiate that, you find the derivative of that. Okay, and then I'll give you the derivatives of 1 over I is negative 1 over I squared, and then you divide them, put a negative sign, then you have the modified duration for the perpetuity immediate is 1 over I. And the Macaulay duration is 1 over I multiplied by 1 plus I. So these are somehow I kind of forget that for perpetuity and perpetuity immediate, we would have different duration calculation. The difference is like a factor of 1 plus I, vice versa. And but in the text, this is what's being offered. The Macaulay duration calculated based on the weighted average of payment time. In the end, it's the same answer for the perpetuity immediate. It's the same answer. That was this example. All right. So this question I had on the clicker has only 3 payment times. So it's going to be a weighted average between 2, 3, 4. And that's why you can see that all the answers were 2, 3, somewhere lower or higher than 2 and 3. So let's try to go through the calculation. Here. a little reminder that today is a class day, but tomorrow, the whole day, whenever you are ready, I will post it today, but it should open like tomorrow in the morning until late in the night, so it should be the whole day. Anytime you find time to work on this. You can even work on them like early morning, 3 o'clock to get it out of the way, if you're up to it. Anyway, so the time is flexible. Another thing is because I explained it today and then the material is on the test tomorrow, it's kind of like too hasty. So if you feel like that's not enough time, feel free to contact me with questions. So I should be open for like phone calls or email tomorrow if you have any question, any concern about test 3 that you are working on. So my whole point is to have that test 3 more like a required homework that you have to do. So once you do that homework, you kind of be more familiar with the duration, immunization concept. Also, test 3 has a solution video. The practice question has a solution video online on Georgia View. So you can watch the video to kind of see some example that you might see on the test. So that was test 3 in today's content, April 24, and then that's video review for test 3. You can find the same video in test. The practice question for test 3 is over here. This is the practice question. That was a video. So that if you need more example, it's in there. I try to go as detailed as possible. Okay. Any question about the test? Let me know if you have any questions or concerns. Let's move on to the attendance question. We're gonna try to find the weighted average of the payment time. So then we're calculating Macaulay duration. It's weighted, you take the payment time. In this case, the payment time are 2, 3, 3, and then 4. So each one should be multiplied by their corresponding weight. So what was the weight? Is the total present value, as in the denominator. The numerator should be present value of that cash flow. At time 2, the cash flow is for 40,000. So you go 40,000. We want to find the present value of that 40,000. Multiplied by the interest rate is 7%, 1.07 to the power of -2. Okay, plus this times 3 weighted average. So the weight is total present value. And then the present value for that cash flow is 25,000 times 1.07 to the power of -3, plus the payment time 4 has a payment of 100,000. So now the total present value has to be the present value of all 3 added together, but we'll do that. 100,000, 25,000 multiplied by 1.07 to the power of -4. Okay, and you should know how to calculate the total present value, right? The total present value is supposed to be all 3 of them added together. This, added this, all added together. It's big summation in the denominator. So that's how you calculate it. Let me see if you already have your answer. Calculation for the Macaulay duration. Still waiting for it to respond. Okay, thank you. Let me know if you already have the answer. Okay. Sorry, thank you. So 3.3. That's a calculation practice of calculating Macaulay duration. If you want to know the modified duration, it will be the Macaulay duration divided by 1 plus I. In this case, once you get that 3.3, you will divide it by 1.07. That will be the modified duration. I'll put writing. I just want to mention that you kind of know that the multiplied duration will be slightly lower than the colloid duration. So today I want to talk about immunization. I think I started mentioning it last time, right? So let's talk about what exactly is immunization. It's not the medical term immunization. The term immunization is immune to something. In finance, you want to be immunized over risks. When you talk about money, one of the risks would be what if the interest rate change? Okay, so what we want to do is being able to cover any liability that's in the future. So here we have an example. Suppose you need to pay 50,000 5 years from now. Now you want to make sure that you have cash to cover that liability. So instead of imagine or thinking that reasonably you might have that money, you want to make sure that you have that money now. There are a couple of possible investment opportunity. There's a 5-year zero coupon bond. There are 3-year zero coupon bond. There's 7-year zero coupon bond. So one of the options will be you can buy the 5-year zero coupon bond enough so that the future value cover that 50,000 debt, 50,000 liability. Another option maybe at the time the 3-year zero coupon bond, 7-year zero coupon bond has a lower have a lower price compared to the 5-year zero coupon. So maybe like we can invest in a 3-year zero coupon bond or the 7-year zero coupon bond in order to cover the 5-year liability. So the question will be how much of those different those zero coupon bond we should invest in order to cover the risks. Okay, so there are things we have to consider. This is why we need immunization. If you are just go ahead by the 5-year zero coupon, there's nothing to worry about. We don't really have the risks in there, except the current costs might be high. So the reason that we want to invest, maybe because there's chance for us to save some money currently. So, but then there's the risks. One thing is if you buy the 3-year zero coupon bond, and then you have a 5-year liability. So by the time 3 year, your bond mature, and you want to make sure you want to reinvest your investment so that at 5 year you still have that much money. So that is if the 3-year change to a 5-year cash flow, you will wish the interest rate to be high, right? Because you're investing. So that's one. So if you're investing in the 3-year zero coupon bond, you want in 3 years. When your bond mature, you want at that time the interest rate to be high for you, and that is sometimes unrealistic. Right? What if by the time 3, the interest rate decrease, and you may have to pay money to cover your liability? Right? You might lose money. Another situation is what if you invest in a 7-year zero coupon bond? Then you were supposed to hold longer than the 5-year. So by the time 5, you have to sell your 7-year zero coupon bond to cover your 5-year liability. But the bond that you hold in your hand is your asset. So by the time you want to sell it, then you want lower interest, right? Because you want to discount back to time 5. So in that case, your value, you divide by 1 plus I squared, because 1 plus interest rate squared. That's why if you divide by the interest rate, of course you want lower interest rate, right? But what if at time 5 somehow the interest rate went high? So if you want to sell your bond, you will have to pay more money, right? If the interest rate somehow went higher. So there's a worry about the interest rate in the future when you are trying to materialize whatever asset in your hand. That's what we are calling interest rate risk. So one thing we can do is combine them. So here we have, I draw a little picture, put this page earlier. So there are 2 scenarios. If you get 3-year zero coupon, you want the interest rate or the forward rate in 3 years to be high. But if you have a 7-year zero coupon bond by time 5, you want to discount back to time 5. That's when you want to wish your interest rate to be low. So either way, you have worry. So we decided to buy a combination of it. So here we have, this is an investment plan. You would buy the 3-year zero coupon bond, we have we have a redemption value of 22,675.7, and we also buy the 7-year zero coupon bond that's 27,562.51, right? Each are priced using the yield rate of 5% annually. That's kind of unrealistic that the two bonds are using the same yield rate, but for now, we'll just settle for that numbers to make it easy for calculation. So 5% interest rate is all the interest rate for every investment right now. So what do? We want to use the combination of these two to cover our 5-year five-year liability. Still, at the time 3, you have your 3-year bond, the 3-year zero coupon bond mature. You have to turn that into another investment so that the money will keep growing until time 5. So that's the concern about in 3 years, what is that interest rate? So here at the bottom, we're talking about how things can plan out, and to see that with this kind of investment combination, and you can call that a portfolio, we will be able to cover risk. No matter what was the interest rate by time 3, after 3 years, time to work out you have your maturity of your 3-year zero coupon bond, you turn that into an investment of a 2-year zero coupon bond. So then at 5 year, you have sufficient fund. So imagine at time 3, the interest rate is 20%, 5%, or 1%, and what will happen there? Okay, so let's look at what happened now. So in the original question, we were buying a face value of 22,675 for the 3-year zero coupon bond and 27,562.51 for the 7-year zero coupon bond. Their total present value actually is equal. So we divided by the 1.05 to the power -3, 1.05 to the power -7 for both of these two, which end up getting this. So you will have to pay money to buy the 3-year zero coupon bond, and 7-year zero coupon bond. This is what we're facing. So you will have a positive cash flow at time 3 and time 7, but you're gonna have a negative cash flow, which is the money you pay for the bond. Are we okay so far? All right, so that's what happened right now. I write down the time 0 interest rate, which is 5%. Let's look at what happened when the interest rate went high to 20%. Let's say at time 3, somehow the interest rate rise. Remember, we worry about interest rate rise for the longer investment, and it's okay for the shorter investment. Well, I think it's the other way around. For the shorter investment period, we want a lower interest rate. We want higher interest rate for the shorter interest and lower interest rate for the longer one. So either way, let's look at the calculation. Imagine at time 3, interest rate is 20%. So now that won't affect our zero coupon, the 3-year zero coupon bond, because for the 3-year zero coupon bond, the cash flow is all set, right? It's already being set and in paper. So you get your 67.75 cash flow, but it changes the cash flow for the year 7, because our plan is at time 3, we're gonna sell out the 7-year zero coupon bond to get cash. The cash we get from the 3-year zero coupon bond and the 7-year zero coupon bond all become a purchase for the 2-year zero coupon bond. So then the total cash flow at time 3 will be 0. Are we okay there? And so with this, we realize that the red one, the number that I have for the 3-year zero coupon bond now is cash, and can compare the original imagined cash flow is this. Now the time 7 is no longer there. It becomes the cash flow at time 3. And that number is calculated using your time 7 cash flow divided by 1.2 to the power 4 to get that value. And then those total cash flow is here. They were being purchased into a 2-year zero coupon bond using the 20% interest rate. We would have a time 5 value of this. Are we okay there? So we have a combined cash flow, and that's a negative because we're buying. Those money all become a purchase of 2-year zero coupon bonds. So then we will have a positive cash flow at time 5. That kind of cover the 50,000 that we have. Are we okay? So it looks like a higher interest rate was okay. Now, The second scenario is what if the interest rate didn't change at all? In that case, you do the same, your 7-year zero coupon bond material, well, you sell it for a price based on the new interest rate. And then you combine that with what you have, redeemed from your 3-year zero coupon bond. They end up being the same value because the interest rate didn't change. And now you buy the 2-year zero coupon bond, so that you can have enough cash flow at time 5. So in this case, if a 5% interest rate, they end up having the same cash flow because we're really following the same timeline with the same interest rate. That's why we're same. Combine them and then let the value grow with a 5% increase. At time 5, you have exactly 50,000. That's the second scenario. The third scenario is what if the interest rate drop? All right, that is going to severely increase the money that we get from selling the 7-year zero coupon bond and combined with the redeemed value from the 3-year zero coupon bond. And now we're buying the 2-year zero coupon bond, so we can cover the time 5 liability, and that's what would happen. So if you have an interest rate of 1%, so the times 7 cash flow is materialized or sold for this much, and combine those cash flow to buy the 2-year zero coupon bond, so we can cover the time 5 liability. And we have a little bit of money extra there. Any question? So the scenario is if the interest rate stay the same, we barely cover, because that's what we did our calculation, the original calculation based on that. We want to match up exactly that cash flow. This is how we determine the initial purchase. But whenever the interest rate change up or down, we end up always have a little bit extra cash, right? When the interest rate change different from 0.5, we actually went up as far as the total, the net cash flow. Any question? So this is the immunization. This plan, we end up like we're better off either way if the interest rate change. Okay. So what happened here? What we're doing here is matching the cash flow and also matching the duration. So we're going to try to look at another example, say to determine how do we match the liability. So if you need to pay. Like this one, we only match one liability, which is easier. This one, the example that we did here is called a full immunization, where you have a single liability, you have an earlier asset and later asset compared to that liability. So whenever whenever you want to achieve a full liability, the liability is in the middle, a full immunization. Then you have 2 assets, one before, one after. That's the situation we can obtain full immunization. Question. But then there are situations we do not have a single liability. You may have several liability, and then situation a bit more complicated. And in this case, number 1, we want to have a sufficient asset to cover all the liability. So here we have we need to pay 10,000 in 6 months, 50,000 in 12 months, and 12,000 in 18 months. So we want to purchase exactly. So we are just trying to cover the liability in this case. So then we have 6 months zero coupon bond, and then we have 12 months 6% par value bond with semi-annual coupon, and then we have 18 months 5% par value bond with semi-annual coupon. So this is a little different than earlier. Instead of zero coupon bond, which only available for shorter term. So ideally, the most common kind of longer term bond all have semi-annual coupon. So now, what if that's the situation? How do we match the liability? So we want to match exactly the cash flow there. If we match exactly the same cash flow at the same time, they will have exactly the same duration, right? But then the design will be a little bit different, a little bit more detailed. So here is how we match everything. So the original question goes, we have those liability, and I should put them all in negative sign, but on the timeline, and those are the cash flow for the liability. So we're going to match our asset to be having the same cash flow. These are the 3 the 6 months zero coupon bond, 12 months 6% par value bond, 18% 5% par value bond. So to match the cash flow, realize the 6 months zero coupon bond only have one cash flow at 6 months, and then the 12 months par value coupon bond have cash flow at time 6 months, 12 months, and 6 months and 12 months. The 18 months has cash flow at 6 months, 12 months, and 18 months. Because the 18 months is the only one that has cash flow at time 18. So then we should match that one first, right? We make sure that our 18 months par value bond actually have enough cash flow to cover the 25,000. So we're gonna do that first. That's the entire solution in the book. So a little bit longer to read. So here's the plan. So look at the 18 months, 5% par value bond. 5% divided by 2 is 2.5%. 2.5% multiplied by the face value. That's the amount of the coupon. So you have 2.5% F, 2.5% F, 2.5% at all three times. And then their final face value payment at time 18. So at time 18, the actual cash flow is 1.025 times the face value. And then we want that cash flow to exactly equal to 25,000. That will allow us to solve for the face value, and which end up having the 24,390.24. Are we okay with this? All right, so then we know how much the F is supposed to be. And then now we know the entire cash flow. And so we know the F, we have our cash flow for the, if you multiply 0.025 is F, you get 609.76. Now you have the whole cash flow at 6 months, 12 months, and 18 months. The 18 months is actually the 1.025 F, being F the calculated value. So now the last cash line, that's the last timeline of the cash flow, is the targeted cash flow for that 18 months coupon bond. Now let's look at the 12 months par value bond. All right, so now we are able to cover the 18 months liability and asset match up. Now we want to match what happened at 12 months. The 18 months cash flow already have a cash flow of 609. So we only have to cover the remaining portion. Are we okay there? So subtract those two. We know that we have to cover, if you subtract, it's actually 14,390.24. But the actual cash flow for the 12 months, 6% par value bond, the 6% divided by 2 is 3%. So 3% of F is the coupon. And then at time 12, you also have the F. So the actual cash flow at time 12 is 1.03 F. That's supposed to equal to the remaining portion we want to pay at 12 months. That allows us to calculate the F. Once you have the F times the coupon rate will give you, you times the 0.03, give you 419.13. That's the coupon value. So the cash flow for the 12 months is 419 at time 6. And then 1430.24 at time 12. That's the cash flow of the 12 months one. And then you can see when you combine this with the 18 months one, you now cover the 15,000 at time 12. And that leaves us one more thing to do. Right, so those are covering up the liability at time 12. The only thing left, we combine, and you can see we have cash flow at time 6 from the 18 months cash flow, the 12 months cash flow, and that is already 1,028.89 from the other bond. The only thing that we have left is for the 6 months cash flow. We want to cover the 1,000. So you're going to take that 1,000. Well, it was supposed to be 10,000. Yeah, you take that 10,000 minus the 1,028.89. The remaining portion supposed to be how much investment in the 6 months bond. Any question? So that kind of back where you always go for the longer time frame, since that's only available in one of the assets. So that's kind of reversing everything we've done from 18 months back to the 12 months back to the 6 months. That's kind of short. This one is a little bit not as clear, so I try to go through each step to explain the process. Are we okay? All right, so far we talked about how to match the asset, what does a full immunization look like? So now we're gonna explain some of the key idea. the most common liability that we had, they were the Reddington immunization and full immunization. So we're gonna try to build that by like function side effect point of view. So first you want to set up a function, it's really called a surplus function. It represents the total present value of your asset minus total present value of your liability. So we use AT for all the asset at time t, and we use LT for liability at time t. So each one is being discounted back to time 0. So SI equal to summation of AT time 1 plus I to the power negative t minus the LT time summation of LT time 1 plus I to the power negative t. Any question? So that's SI. So basically the SI is the present value of all the total present value of the asset minus the total present value of the liability. And if you want to match them up, they should equal each other, right? So if we barely cover the liability using our asset, then SI equal to 0, right? Even though SI is supposed to be a function of I, but if we're matching the asset and liability, SI equal to 0. Even though, but when I change, it might not stay at 0, but we certainly want it to be 0 at one point, right? And then we try to study some behavior of this function SI. Okay, so at the calculation time I0, which will be the current interest rate, we want SI0 equal to 0. That means the current value of the asset equal to the current value, present value of the asset equal to the present value of the liability. We also want the derivative of S at the S function equal to 0, because if the derivative equal to 0, that means say the duration of the asset equal to the duration of the total asset equal to the duration of the total liability, right? That would be matching the duration, matching the asset. So S equal to 0, match the asset and the liability present value. And S prime equal to 0 is matching the duration of the asset and duration of the liability. One more thing, we want the second derivative to be bigger than 0. Because if the second derivative equals 0, the function SI concave up. Yes? A concave and equal to 0 at right in the middle, meaning that xi0 is the lowest point nearby, right? So in an area close to I0, the function concave up, if the I change slightly larger or slightly lower, because functions concave up, you will have a positive SI value, right? So that means if the interest rate change slightly, you're only being better off. You will have the total asset being higher than the total value of your asset is higher than the total value of your liability. I hope that kind of makes sense. Any question? So satisfy all three. S I equal to 0, S prime I equal to 0, S second double prime I bigger than 0. That's the so-called Reddington immunization. So this is kind of a short proof of why this is true. You can see if the I change slightly by the Taylor expansion as I equal to 0, S prime I equal to 0, so S double I is positive. If I change slightly by H, and then you have a positive S function value. So that kind of verification of why this is important to have a positive second derivative. Any question? All right, so here, this is being called, this condition is called Reddington immunization. If the Reddington immunization hold, then we are immunized against small change in the interest rate. So interest rate change slightly, it doesn't matter. Now, if the Reddington immunization is true, then the total present value of the asset equal to the total present value of the liability, and also they will have equal duration. Doesn't matter Macaulay duration or modified duration, they're all equal. Another thing is the second derivative being positive means that the Macaulay convexity is larger than the Macaulay convexity of the liability. That is really the second derivative that we're talking about there. And we didn't really focus on the convexity, but you can definitely study the second derivative for it. Any question? So especially that's really about the concavity of the value function. Okay, so let's look at a couple examples. How do we achieve it? This is the fourth example on 9.6. We're talking about L&P body insurance company is obligated to make a payment of 120 in exactly 4 years. In order to provide for this obligation, their financial officers decide to purchase a combination of 2-year zero coupon bond and 5-year zero coupon bond. So the liability is at time 4. We decided to make purchases. So that's asset at time 2 and time 5. So that seems to be similar to our plan for the full immunization. Each of these sold to yield annual interest rate of 4.5. How much of each type of the bond should be purchased so that together with the liability in 4 years, the zero bond constitute a portfolio certified Reddington immunization condition. How does this immunization result? Okay, so we're going to try to analyze how much of each one. So let's call them A and B. So basically, A and B will added together the investment for these two kind of bonds total equal to the total value of the present value. So you're going to take the 120,000 divided by 1.045 to the power 4 to find the total present value. So A plus B equal to total present value of that the year 4 liability. On the other hand, the weighted average of liability should equal to that the duration of that liability, which if you only have one payment and that liability for the duration for the liability is 4. Now the duration for our investment, since one is a 2-year zero coupon bond, one is a 5-year zero coupon bond. So that's where the 2 and 5 comes from. Yesterday I was making a solution when I was supposed to do a linear combination of 1 and 3. I did a linear combination of 2 and 5, and then it just didn't work out. I realized I was using the wrong number. So 2 and 5 are the time of the payment. The weight for them, the A and B are the present value, and A plus B will be the total present value. So A and B is really the investment at time 0. So this one we don't have to discount it because it's already a present value. So then from the system equation we solve A and B, and you can also calculate the Macaulay convexity of the asset, which is the weighted average of the t squared. So we have time of that would be 2 and 5 are the time, 2 and 5 are the duration. So you would square the 2, square the 5, and then multiply by the weight of each asset. That's A over A plus B, B over A plus B, and then the total convexity, Macaulay convexity is 18. The total convexity for the liability is 4 squared, which is 60. So then the convexity of the asset is bigger than the convexity of the liability, which achieve making the second derivative function positive. So that it looks like this combination satisfies the Reddington immunization. Any question? Okay, so we are immunized against possible interest risk. So the answer will be this immunization did help. Any question? Okay, sometime we will solve making the asset adding up to the present value, and then the total duration equal to the duration of the liability. And then after solving A and B, and then you find out the convexity is lower than the liability convexity, then that would be a problem. That would mean that you find out a way to match the value and match the duration, but somehow the Reddington immunization did not satisfy. So that could be a possible such scenario. At least in this question, it was okay. All right, so this is try to explain what will happen if the interest rate change. The original interest rate was 4.5%. That would be the top one. You have 2-year zero coupon bond and 5-year zero coupon bond. That was the original interest rate of 4.5. Now at time 2, because we have a 2-year zero coupon bond mature at time 2, so we want to make sure that when it mature, the money have to be reinvested. So it's time for reinvestment at time 2. Suppose at time 2, the interest rate rise to 5%. what will happen that your 5-year zero coupon bond, you want to turn that into money. And also your 2-year zero coupon bond already turned into money because it's mature. So now you have total amount of money of 108,000, and then you want to turn that, buy the, well, that would be 2-year zero coupon bond to make sure you cover your time 4 investment. So it turns out at time 4, the 2-year zero coupon bond or any other 2-year investment grow into the 120,000. It has 2.773 more than the intended value, right? The other scenario is, what if the interest rate dropped to 4%? If that's the case, then at time 2, your cash flow from the 5-year zero coupon amount will be a little bit higher because the interest rate is lower. And then in that case, then your combined cash flow is more, but then you have to let it grow based on the lower interest rate. In that case, eventually the combined effect it still covered the 120,000 liability. So this is a graph that illustrates that whichever scenario we're covered, we're immunized against the risks, small interest rate changes. Okay, any question? Okay, so the original interest rate definitely covered, but the new interest rate, that's why you need to consider what will happen. I use this Excel spreadsheet just to cover a different time what will happen. Okay, let's talk a little bit about full immunization, and this is really the timeline. If you have a liability at time T, how do we make sure that we're fully covered, no matter the interest rate went high by a lot or lower by a lot? It doesn't matter. So Reddington immunization only works when the interest rate made a small change. If it's making big change, then things can be unpredictable. So full immunization will guarantee that doesn't matter it changed small or big, we are still covered. So how do we do that? Normally is you want to use 2 assets to cover 1 liability. Now, suppose the liability is required at time T, so you're gonna have 2 different assets. One is before time T, one is after time T. So the UMV in the timeline is the positive cash flow. Let's assume the time is at T minus U and T plus W. Right, to make it easy for finding the derivative, we're using the example using the continuous compounding. Are we okay there? So the present value for this is actually the present value for all 3. And so U discount to time 0 is e to the negative delta, time is T minus U. Now for the L, it's the negative cash flow, e to the negative delta T. That's how you discount it using the continuous compounding back to time 0. And then W is W time e to the negative delta T minus W. Now we can factor common factor from this, and then what you have in the parentheses is really the value time T. Are we okay there? So it looks like because the e to the negative delta T would always be positive, so the only thing we should worry about is what happened, what was the value at time T. At time T, the liability is L, and then the asset U has to grow to time T, so you have a positive factor, larger factor, and then W have to be discounted, so W multiplied by a number lower than 1. So that's the present value calculation part. So we can see that we can determine the quantity of U and W, so that the S delta 0 is equal to 0, and the derivative also equal to 0. So we can achieve the net present value equal to 0, and the total duration, the duration of the liability and asset equal to each other. So the first root equal to 0. Any question? So this can be done by setting up a system equation. Okay, so here we see if you can satisfy that the net present value S delta 0 equal to 0, and then the derivative S prime delta 0 also equal to 0, then we're fully immunized against any interest rate. Why do we see that? Because if you want to find the second derivative of this function, it will always be positive. You see, when you try to find derivative e to the, well, that one always has positive derivative. So don't worry about the e to the negative delta t. So finding derivative with respect to the interest rate delta, this e to the, this is u times e to the delta u times u. So it's going to be u squared. And then this negative L, when you try to find the second derivative, I think that will be zero. And then this one also will be positive when you find the second derivative. So essentially the second derivative of the entire function will always be zero. And that's the reason we want a one, the asset one below, one after. Okay. So that's the so-called full immunization. Any question? So basically the full immunization, the complete part is that you always have to use two assets to circle or to like surrounding one liability. You know what I mean? If you have multiple liability, if you have to cover every single one of them, obviously your asset has to design in a way that it covers them all, right? Right. That's the difficult part of it. The full immunization definitely will be more efficient than the Reddington immunization. Reddington immunization do not have any requirement for the position of the liability and the asset. So this is an example. We're going to talk about how does it work. Most of them end up being a system equation anyway, system of linear equation. So here, suppose it's a similar scenarios. Let's say we have to pay 120,000 in 4 years. So we purchase a 2-year zero coupon bond and 5-year zero coupon bond. Okay, and then we suppose we have a larger interest rate change, 10% or 1%. We want to see if it's fully immunized. Actually, that one is a scenario, right? The 4-year liability in the middle, then you have a 2-year and 5-year, one below, one after, right? That's exactly what is our intention. Once you have the asset, one before the liability, one after the liability, and then guarantee the durations match, the prices, the present value is matched, and they always will be fully immunized. So the position, the timing kind of is part of the design for full immunization. Now we're going to look at what happened if the interest rate did change to 10 or 1%. So if the interest rate went up to 10%, then the 5-year zero coupon bond will be priced at 62,809. Combine those assets to buy the 2-year investment. By the time 4, you have 12,000 more, like way more than 120,000 to cover the liability. Another scenario will be, what if the interest drop way down to 1%? So that really is different from 4.5%. That means you will have a much higher value when you try to materialize, like when you sell your 5-year zero coupon bond at time 2, you end up having that value. And then combine those cash flow, you have more money to buy the 2-year cash flow. But then of course the interest rate is lower, so it won't go as that fast. But still we have enough money to cover the liability. Any question? So this just play out what will happen if the interest rate went up and low by a lot. And it looks like we still have enough money to cover the liability at time 4 because we are fully immunized. So full immunization. Any question? That's another example of full immunization. Basically, let's summarize. Suppose you have a portfolio consists of a single outflow of a single liability, and then you have an inflow before, inflow U at T minus U, W at T plus W. I draw the timeline, just indicate liability in the middle, and then before and after to asset. In that case, what you have to do is solve a system equation. One is for the value at time L. So the value of U, you will let it grow to time T. And then the value of W will let it discount back to time T. So the first equation is a system equation of the time value of money. Are we okay? So the first equation match up the value. Now the second equation is a derivative of the first equation if you think about it. Any question? Derivative with respect to the interest rate delta. So if you find the derivative of the UE delta U, the exponential function will have a changeable, so that there's an actual U. This one you will have to have an extra W, negative W, and derivative L equal to 0. So it's really differentiable side equation with respect to delta and set equal to 0. This is really the value, matching the value in the first equation, matching the duration in the second equation. So what do we do here? We're using the system equation to solve U and W to have enough money to cover the liability. Any question? All right, it doesn't have to be the continuous compounding formula. You can calculate the value of the equation using the compound interest formula. And you just have to set up equation value and then differentiate your equation value with respect to the time. Okay, with respect to the interest rate, not the time. Okay, so let's look at equation example on full immunization. This is the same example on the practice test, so better I'll just include it here as example for the full immunization. So let's say a person have a liability of 6,000 due in 4 years. This liability will be met with payment of A in 2 years and B in 6 years. So that sounds like a plan for full immunization, because the liability at time 4. The 2 is before 4, the 6 is after 4. So it looks like we are going for full immunization. So then the interest rate is 5%. We want to find out the A minus B, meaning that we have to find A and B, and then we could subtract them. All right, so this is a timeline. Okay, so I'm writing the full immunization equation using the compound interest formula. Are we okay? All right, so I'm setting up equation for time 4. Remember, equation of value can be set up at any given time. Most of the time, we write equation for time 0. That's why we calculate present value all the time. But to lower the power, it's easier just calculate the equation of value at time 4. Let's do. Okay, so we draw the timeline and we realize that time 4, the total value will be the negative 6,000, still negative 6,000. And then the asset A will multiply by 1 plus I to the power 2. And then the asset B will multiply by 1 plus I to the negative power 2, because we just come back to time 4. We set equal to 0, so then the A and B will cover the liability at time 4. So basically, if you already have A and B, that at time 2, you let it go to time 4, so you have that much money. And then you also have B, but it's B. If B have not matured yet, you can sell it, right? Sell it for B times 1 plus I to the negative 2. Those are gonna money that will cover the 6,000. That's the plan. All right, and then the thing is that this is our value function with interest rate being the variable. You can find the derivative of it. So with power rule, we find the derivative, we set it equal to 0. The reason that we do that is that once the derivative equal to 0, then the liability for the asset will equal to the duration of the liability equal to the duration. This is duration matching, basically. Or you can do the other way is you're going to have to calculate total value and divide. So I don't want to do all the proportion or the weighted average thing. I follow the function notation here. Okay, so this is imagine the I being the variable, but the I is not the variable. So we can look at the question, the interest rate I is 5%. I keep the I as a variable because I want to be able to differentiate it. So now we have 2 equations and we're going to plug in I equal to 5% and solve for A and B. The whole thing is to figure out a way to calculate A and B. So with that, putting the A, I equal to 0.5, and the second equation become A times, right, the 2 cancel from the equation, since we said equal to 0. 2 cancel, then A times 1.05 minus B times 1.05 to the negative 6 power. Then you multiply both sides, move the B to the other side equation, multiply by 1.05. And then we have this. So you have a relation from equation 2, we have the relation between A and B, and then we can bring the A times 1.05 to the power 4 equal to B, and then replace the B in the equation 1. So now equation 1 becomes this. And we pretty much follow that to solve for the A. Once we solve for the A, then B equal to A multiplied by a factor. B will be able to do B. Once the A and B are solved, we subtract to find their differences. Any question? So when we set up the equation 1 and 2, the rest is all algebra, the rest is all solving the equation. So the final answer should be D in this question. It's an example on practicing how do we match the present value and the duration. Basically, the matching duration means setting your function. This is actually the surplus function, setting the derivative 0. That's the trying to match the duration. Any question? So that's this example. I don't know if you have time. Yeah, we do have time. And this is a last example in the set. Liability consists theory of 15. Oh, that one. 15 annual payment of 35,000 with the first payment to me. So that will be annuity of 15 payment. The asset available to immunize this liability are 5-year and 10-year zero compound. The annual effective interest rate used to value this asset will be 6.2. And the liability has the same present value and duration. So to calculate how much do we invest in a 5-year zero compound. So we need to find the total present value. So then the investment into the two kind of bond will equal to the total present value of the annuity. So any question? If we have time, we can finish this one. Copy this question over. I didn't write down the solution, so I felt like maybe we could spend some time. You guys might be able to calculate this faster. First is we are gonna find out the total present value, and then that's the total present value of that's the Q 15 payment of this by the end of the year. So it's going to be that's our Q. So Q multiplied by A 15. And then 15I, we have the interest rate of 6.2%. So then the asset is 5-year and 10-year zero coupon. Suppose the 5-year zero coupon bond is A, the 10-year zero coupon bond is B. So then the A plus B should equal to the present value. So spend some time calculating the present value. Another thing is we want to match the same present value, and so now that's matched. The same present value of A plus B is the present value of the asset, and then the present value calculation from the annuity formula is the liability. Then let's match the duration. To match the duration, A and B, the 5-year zero coupon bond has duration 5 and duration 10. So the 5 is the payment time for the 5-year zero coupon bond. It's weighted by A over A plus B. And then the 10-year zero coupon bond is weighted by B over A plus B. I mean, A plus B is supposed to be the total present value calculation anyway. Now this should be equal to the duration of the Macaulay duration of that we have to calculate. Macaulay duration of the liability. Any question? So basically we were supposed to solve this system equation for A and B. But this system equation is missing 2 numbers. One is the present value, and that we can calculate, and one is the Macaulay duration that we can do a calculation for as well. So let's see how we calculate the total present value of the annuity. Go like this. The present value of all the annuity. Every year is paid 35,000. It's multiplied by A15. So it's 1 minus the v to the power 15, so the 1.062%, and then raised to the power negative 15, which is divided by 0.062. So that's how we calculate the total present value. This is the annuity Q times A15. Grab the calculator. So we have this value. That's the total present value. It's A plus B. And now we need to calculate the Macaulay duration. Okay, so how do we calculate the Macaulay duration? I don't want to do the derivative thing because I realize this is a long calculation. So I'm going to do the weighted average of the payment time. So we are having 35,000 is the payment, and it will multiply by 1.062 to the power t, and then that's the power negative t. So that's the present value for each of the t goes from 1, 2, 3, 4, 5, 6 until 15, right? That's the and then it's weighted by the divided by the present value, which is this one. Okay, so that's the weight for every t, and you're gonna have a t multiply this, and then we're gonna calculate this for every t value. So it's gonna be a summation of, and then t goes from t equal to 1 to 15. I hope that kind of makes sense. Are we okay? So you can see in this whole calculation, there are some common factors. You can see that these 35,000 divided by this number is a common factor in this calculation. And then this is multiplied by in the, for instance, let's do calculation. So we will have 1 times 1.062 to the power of -1. It's 1. And now we're going to have 2 times 1.062. We have those sequencers. This is a sequence to the power -2. So that's the right value time interest rate to the negative t power. That's a discount. And the division is already outside. These are all multiplication summation. And plus there's 3 times 1.062 to the power of -3. And we have to do this 15 times. Right, let me try to save some time. Right, next up is 4. And now it's 4. And then 5. 5, 6. Right, maybe there's faster way to do this, but here I am doing this until 15. You get an idea. So there's some calculator allows you to enter the sequence. Maybe we can do this calculation in the sequence a little faster, but until all the way to 15. That's the calculation of the duration. We put in all these in the calculator. I wonder if it does calculation for us. There's 14. Monthly. Right, so that's all in the summation, right? That's the adding part. We're basically trying to find a weighted average of the time. And here we are. That calculation should give us the average payment time. Essentially, that's what it is. That's why it's called a duration of the payment. Here we are. That's 6.89. We find out the duration. Are we okay? Back to what we really want to calculate. This number is 6.89. we're solving for A and B. This number is the total value of the present value. A plus B, we put this. Solving for A and B. Any questions? So from this, we can see the second equation goes 5A plus 10B, which will equal to 6.89 multiplied by A plus B. But what's A plus B? A plus B is that the present value calculation. So that we have this. Okay, and if we divide both sides by 5, if we divide this by 5, we'll get rid of this 5, and then we'll make this one equal to 2. And this calculation is going to shorten the relation between A and B. That's the number for A plus. So that will be the A plus 2B, which this. I guess I can move this all calculation to a place for typing. Okay, so now we have this. We already have that A plus B was equal to the total present value. Right, so having A plus B and then having A plus 2B, you can subtract them to find out B. So once we get one side of the equation a little bit shorter, it won't be too difficult to find the rest of the minus this number that allows to find out the B. Once we find out the B, the total value minus B, which will be the A. A and B, if you find one and then finding the other one, it should be algebraic. It should be. Find that one is our B. So A would equal to, we know that A plus B is this number, and you subtract the B value to give you A. And that's finish this. And that will be what we're trying to find out is the A, right? Finding the 5 here. I hope I didn't make any mistake in the calculation. So our number I have so far is this. Sure. Did I make a calculation error? All right, I think I do have the solution. It's one of the bonus questions I put on the test. So I already have the solution yesterday, but I didn't work out the detail. Here are the solution. Copied over the solution in the book. This. Okay, so that's the present value calculation. Now we have the duration that was 6.89, and then we set it. So that was this. Oh, that calculation was really short, and you can see. Must have done something wrong in my process. But that's the whole plan. You can redo the calculation. If I made any calculation error, I can go back and double check the calculation. 5A plus 10B. And I divided by 5. 5A plus 2B. Right, I think you can work it out and maybe make it better. We can spend more time working out the details. So if we try to redo it, it would be this is the A plus B, and then we had the second equation which goes a 5A plus 10B is equal to 6.89 multiplied by. Okay, and then divide by 5, it will turn this into 8 plus 2B. I still don't realize what was the calculation error. Might be an accuracy thing because it's essentially not 6.89. There's a few decimal more than that. See, that's what I got earlier. Just comparing my answer with the solution. Okay. I don't see any calculation error in the process, but anyway, that was a textbook solution. Essentially, the final answer lead us, the closest answer we can get is still the same one. It's the, any questions? So this question, because the duration ended up being a little bit difficult to calculate, so we're not doing the derivative of the surplus function anymore. Instead, we calculate directly what is the present value and what's the we'll call it duration, which is weighted average of the payment time. So they essentially there are two ways when we consider duration. The Macaulay's duration is weighted average of the payment time. But if you do have the value function, it's the negative derivative divided by the value function. I think that's pretty much all we need to do for today. That's talking about different type of immunization. Basically, there are two that we mentioned. That would say practice question that we had on the test three sample question. There's a sample test three that I posted. So we're going over two types of immunization. The Reddington immunization is when you have the surplus function that may or may involve more than one liability and more than one asset. So the Reddington immunization is a general method. We want to make sure that the total present value of the asset minus the total present value of the liability equals 0, and the derivative also equals 0, and the second derivative is positive. So that's the idea of the Reddington immunization. The full immunization achieve the same thing as the Reddington immunization, but it required that the one liability is being covered by two assets, one before the time of liability, one after the liability. So the only thing that we have actual in full immunization is a timing, right? That's the actual part. Because of timing, the second derivative being positive is ultimately guaranteed. And that's why we don't have to calculate the second derivative because it's fully immunized. Any question? For chapter 8 and 9, there's no additional assignment. So our homework assignment on web work went all the way up to chapter 6, 6.5, and 6.2. There's no assignment on chapter 6, chapter 7 and 8. But 8 and 9, I do assign some practice questions, but we won't have time to collect them or complete them online. But there's other practice question if you want to understand, like chapter 8 is mainly focused on swap rate. There may be some topic about forward rate calculation, swap rate calculation, and there are a few arbitrage example, but if you're interested, you can look them over. Those are practice questions for chapter 8. Feel free to let me know if you have any question. I can help you solve them. And I also posted a practice question for chapter 9, just so we have something to practice our understanding. And feel free to mention your question if you have an issue. There are calculation duration in 9.2 assignment. There's a determination of a plan for immunization in a 9.6 assignment. In the middle, this is a summer assignment I assigned for my other finance management class. I had one of these in the summer, which is why that was a fully online class. So I don't have to worry about the pace. I assign all of them at the same time, and they have to do it. That's why I was assigning way more homework in that summer. Those are those assignments. But anyway, that's pretty much for today. And then feel free to mention any problem or issue when you were working on the test week question. I consider that for tomorrow, the test week kind of like a preview of the final exam because it contains everything that we've done after chapter 4. If you have any question of the concept for immunization or swab rate, feel free to send me an email. I'll respond so you can finish them. The main thing is to get it done. So as long as you understand and you get it done, and you will get the credit for test 3. Another thing is having one more test made it more of a variety of questions instead of only have a small portion of formal assessment. So that's it for today. Thank you.